In this video, we're going to start off by doing a type of problem we've already done before, where we take a function and sketch its domain first of all, then make a sketch of the function. But then we're going to do something a little bit different with the function after that. So to start with, we're taking this function here, f equals the square root of 25 minus x squared minus y squared. So we, of course, know that we need to have what's inside of that square root. That needs to be greater than or equal to 0, right? And so if I move the x squared and y squared over, then I get this. Now, if there was an equal sign right here instead of an inequality, that would be a circle, right? And of course, we still get a circle, but because of the inequality, we know we're going to shade the entire region inside of that circle to obtain our domain. All right, so we'll make the best circle we can here. And it's supposed to have radius 5, but I don't think I spaced my tick marks out quite the same. And let's see, looks like we need a little work over here. This looks pretty bad. Okay, good enough, I guess. And so, of course, we're going to then shade everything inside of it, right? So this is the region in the xy plane that will output z values for our function. Another way of putting this is that basically this is the shadow that our surface is making in the xy plane, is another way to look at it. So that means that one of the traces that we would need to sketch the function is already done for us, right? So the xy plane, that trace, that is just going to be x squared plus y squared equals 25. And so I can come down here and try to put 5 tick marks on each axis. And there's that domain we just sketched in the xy plane. All right, but what about the other traces? How about the yz plane? Well, that means we're going to set x equal to 0, right? So we're going to have z is equal to the square root of 25 minus just y squared. So that means z squared equals 25 minus y squared, which means y squared plus z squared equals 25. Well, what do you know? We have another circle, right? But this time it's with the y and z variables. So go up to here and sketch in the yz plane a circle, or a half circle, I guess, what I'm really doing, right? Because this is only the top half, because that's positive, right? Just the top half. And then, not surprisingly, in the xz plane, we get the same thing. So z equals square root of 25 minus x squared, which is z squared equals 5 minus x squared. Okay, so then we also can connect things up here and back there. All right, and we can kind of clean things up a bit here, I think, to make it look a little bit nicer. But what it comes down to at this point is that we know that we are producing the top half of of a sphere. All right, so there's our function, there's our domain, and on the next page is the new thing I want to do. So it gives us a definition here. It says that the level curves of a function of two variables are the curves with equations fxy equals k, where k is a constant in the range of f. So in other words, remember f of xy is just a z value. What we're going to do is we're going to plug in different values of z and see what curve that makes in the xy plane. Okay, so we're just going to do a couple of these and then we'll put it all together and kind of see what we've created actually means. So it asks us to do this for k equals 1, 2, 3, 4, 5, right? And from the last page we know we're working with this, right? Square root of 25 minus x squared minus y squared. So, so let's go through and do each of these. Let's do k is equal to 1. So I'm literally just letting the f or the z be 1. But if I square both sides, then I get 1 equals 25 minus x squared minus y squared. And then rearranging, I get x squared plus y squared equals 24. So of course, what is this? This is the circle with the radius equals the square root of 24, which is approximately 4.9. Okay. All right, so that's k equals 1. K equals 2, same thing. Set 2 equal to the z value. So square both sides, so we get 4 is 25 minus x squared minus y squared. Move the x squareds and y squareds to the left, move the 4 to the right, and you get 21. So this is, again, a circle with r equal to the square root of 21, which is about 4.6. And so you can imagine that we continue this process and the detailed work doesn't really change, so I'm going to kind of skip some of those steps. If k equals 3, what we end up with is x squared plus y squared equals 16. So that is a circle with radius 4. If k equals 4, then we have x squared plus y squared equals 9. So that's a circle of radius 3. And if k equals 5, then we have x squared plus y squared equals 0. And so, of course, radius is 0. So all we need to do to sketch these things that we call level curves is to sketch a bunch of circles in this xy plane here. And the most that we ever go out is out to 4.9. So let's go ahead and count out 5. Okay, and then we can start making some of these curves. So 4.9 is just about out to 5. Right, and then I can make my circle, and I'm just going to do this using a dashed line so things don't get too cluttered up here. And I'll use different colors to represent the different level curves. So this one I'm sketching here fix that up. That's this k equals 1. All right, so there's my green one. All right, so then how about in red? We do k equals 2. Well, that has a radius of 4.6. That's still got a fairly large radius here. It's going to be pretty close to that other circle. All right. And let's see here. How about yellow for k equals 3? So that's going to put us here. Okay. And then let's see, I guess we'll do black for k equals 4, which is going to be r equals, oh, excuse me, I guess I messed that up. My k equals 3 should have a radius of 4. So that's okay. I'll leave the circle yellow. My mistake. So my radius of 3 is my yellow one. I'll do this one in black. So that's where k is equal to 4. We're just about there and ready to actually work with these. All right, and then lastly, I'm out of colors. Well, I guess I can do blue for k equals 5. That one's got a radius of 0, so that means it's just kind of a dot in the middle, right? So right there are 5 different level curves for this function. Now the way to interpret this is that level curves tell you a curve, they give you a curve where in the domain, in the xy plane, the z value does not change for the function. Okay, that's why it's called a level curve. It stays level in terms of z values. So a nice picture to go along with this is down here. So down here is the sketch of the level curves for this surface here that's, in three-dimensional space. But these level curves are sketched in the xy plane. And they are the places where the z remains constant on the surface, and you can see those sketched out on the surface. So you take these curves that are on the surface and project them down into the xy plane. And that's what level curves give you. And the advantage to this is it gives you information about a three-dimensional function in a way that's maybe a little bit easier on the brain than if you were to look at the surface itself, right? Because we're very used to getting information from two-dimensional graphs. We're still trying to get used to getting information from three-dimensional graphs. All right, so that's the application of it. Now, I kind of wanted to give a nice look at what's going on with a little bit better picture than the ones I could draw here. So let me open up. Here we go. So essentially, if I do this right here, and I just look straight down on my xy plane, this is essentially what I've just sketched, right, with those level curves. And so what does it really mean? It means that if I then give those curves the height that should be given to them according to their z value that we used, then this would be the height of those curves. And so then if I actually graph the function in the program here, what I should see is that these curves fit perfectly onto that function, and it kind of looks like they're forming around a sphere, right? So it's looking good so far, but then if I type this in, square root of 25 minus x squared minus y squared, then sure enough, there's the top half of our sphere, and I can clearly see that those curves are lying right on that sphere. And the other thing to notice is that you can tell when a function is steeper versus when it doesn't change its height as quickly. Let me take this away again. by how close the level curves are, right? So notice the level curves are much closer out toward the edge here than they are in the middle. And so that corresponds then to a quicker increase in height. And I should be careful how I say that. We graphed level curves that were the z values were equidistant apart, right? So if you graph those z values so that they have a uniform distance between each other, whether that be a difference of 1, 2, whatever, and then you see that certain curves are closer together than other curves, that's when you can tell that you've got a steeper part of your curve versus one that the z values don't grow as quickly. All right, so let's do an example where we just work with the level curves for a function. We're not even going to, we're not even necessarily going to show what the actual surface looks like. Now, those of you who've ever used contour maps are just level curves. So a contour map is one that you might use, especially when you're, you're going to like do some hiking and you're going over some terrain with a lot of elevation change. Then a contour map's really nice because you can take a look at the area that you're hiking in, and you can see how fast you're going to have to climb or descend, right? So if you have contour lines that are really, really close together, you know that you're going to either have to climb or descend a really steep region, whereas if they're further apart, then you know it's going to be a more gradual, easy hike for that part of it. All right, so here's our contour map. So we can make all sorts of estimates for function values based on this. So it asks us to give an estimate for g of 2, 4. Well, all I got to do is find where 2, 4 is here. And I can't tell exactly what the value is, but what I can tell is that it's somewhere between 10 and 20, right? So, there's really not a perfect answer here, but I'm going to call this 13. Okay, approximately 13. Other guesses are just as good, but the key is they better be somewhere between 10 and 20. Give an estimate for G evaluated at 9.2. So 9.2, that one looks like it might be falling right on this contour line of 10. So I think that the function value is probably 10, or the height is probably 10 right there. So for approximately what values of y does g of 7y equal 20? So the idea here is we are fixing 7 in place, right? So that is stuck at 7. So they're saying what values of y does the function equal 20? So that would be here and here. And I can look over to the side here. That looks like it's probably about 3. And up here, let's call it 9. Right? So just following these over to the y-axis and seeing where those points are at. Part D, similar. For what values of x does g of x equal 8? Or sorry, g of x8 equal 20? So we're going to do the same thing, but we'll draw a horizontal line this time. And so let's see, when it equals 20, we're right here. So let's see, let's call that, it's a little bit more than 2. I don't know, let's call it 2.2. And then I would say that the other one would probably be about 9. We'll call that 9. All right, then lastly it says, for approximately what values of y is it true that the function when x equals 5 is between 10 and 30? All right? So we can do a similar picture as we did for these last couple. So since we're talking about only x equals 5, we'll draw this vertical line here. And we want to be between 10 and 30. So let's use a different color here. So here's 10 and here's 30. But in this little region past here, it's more than 30, right? Within this top, or this one that's right in the middle, the elevation gets above 30. So then afterwards from there down to there. So we have this region and we have this region here. So my best estimate is I might call this 3 or so, and I might call this one, well, I don't know, 6.5. And then this one here, I think I might tend to call 7.5. And then this one here, maybe 9.5. Again, I'm just estimating. So your answers might be a little bit different than mine. But we'll say that y being between 3 and 6.5 does the job, and y being between 7.5 and 9.5 seems to do the job as well. All right, so here's where we're going to actually introduce something that's even harder on the brain than three-dimensional surfaces, and that is functions of 3 variables. Now, if you have a function of 3 variables, that means that your function value depends upon x, y, and z. And then the function value itself we know is a variable, right? So just like with three-dimensional objects are functions of 2 variables where the function is the z value. So here, when we have a function of 3 variables, that function value is a 4th variable. So now what we're technically doing is we are looking at functions that don't live in 3-dimensional space. They would actually live in 4-dimensional space. And that's difficult because now we can't really picture that anymore, right? So what we want to do is find the domain of this. Okay, well, we know the domain is whenever what's inside of the square root is greater than or equal to 0. So we're saying z is greater than or equal to x squared plus y squared. Now we know already that z equals x squared plus y squared is a paraboloid. Okay, so that's a paraboloid. So let's start by graphing this paraboloid. Okay, so we know that it's at the origin. My traces in the x, y, and z, y plane just simply give me, I'm going to make this kind of a little bit more of a rough sketch. I'm going to put a lot of detail work into it. All right, call that good enough. A nice circle around all this. So there we go. Okay, so there's our paraboloid. A little erasing there so it's a little more accurate. Okay. All right, so there we go. So the point is it's a paraboloid. Now, the tricky part here, and I'm going to change colors so that I actually preserve some of this, some of the integrity of this picture, is we want the z values to be greater than or equal to x squared plus y squared. Or in other words, take all the z's that are greater than or equal to the paraboloid. So what that means is we want to fill the paraboloid in. If that makes sense, right? So everything inside of the paraboloid, right? Because what is this? Because the surface itself is, think of that as the x squared plus y squared, and then we want all z values that are above that. So everything that's within the paraboloid should be included in the domain. So this is all just to show that this first example, when we had a function of two variables or a three-dimensional surface, its domain was a two-dimensional sketch. Now, if we're talking about functions of three variables, then the domain is a three-dimensional sketch. This is really interesting. So you're going to be able to graph the domains of functions of three variables in three-dimensional space, but then you won't actually be able to draw a picture of this surface itself because it lives in 4D space and our brains just don't do that. And by the way, as this is kind of our first introduction to functions of three variables or 4D space, just to kind of help you understand, this is not just abstract and you know, just a mathematical anomaly that isn't useful. Just think the universe that we live in really is four-dimensional, right? So if you let the fourth dimension be time, then you know, you may have heard the term space-time, right? We're living in space-time essentially. So we actually live in a four-dimensional space, but what the difference is, of course, that fourth dimension of time, you know, we don't sketch a picture of it, right? And so we see things in three dimensions, and then there's that fourth dimension of time that's also involved. So we really do live in 4D space, so it's important to study it. All right, so for a function of two variables, we had level curves, right? And so you kind of think of curves in the xy plane versus the domain of a function of two variables that was in the xy plane, right? Just like we had here. Here was the domain in the xy plane, and on the next page, level curves in the xy plane. So here we had, in three-dimensional space, a surface that's, you know, in this case been filled in for the domain, but it's a region of three-dimensional space going along with what would be the analogy of a level curve? Will it be a level surface, right? If we have functions of three variables. Because if I set the function value equal to a number, then you still have three other variables here. So we'll take, in this case it says, what is the level surface for this function here? So that would be, let's not use yellow, sorry. So that would be 0 is equal to x squared plus y squared minus z squared, which is z squared equals x squared plus y squared. And we can go ahead and look down here, and you'll notice that this takes on the form of a cone. Okay, so these forms right here match each other. So we'll just make a note that the level surface for this function equaling 0 is a cone. Okay, so what about when k is greater than 0? So if k is greater than 0, then what does f of x, y, z equal to k look like? Well, I'll just set k equal to x squared plus y squared minus z squared. Okay, and then let's go down here. If I look at my little cheat sheet, everything that involves x squared, y squared, and z squared all is equal to 1. Okay, I can do that pretty easily. I can just divide by k everywhere. That's no problem. So I'll have 1 is equal to x squared over k plus y squared over k minus z squared over k. So what is that? Well, that's going to be, if I move down here a little further, that's going to be this thing here where we have a hyperboloid of one sheet. So that's what happens when you have x squared and y squared being positive and the z squared being negative. So we'll write that out. This is a hyperboloid of one sheet. Okay, and then finally, if the k is positive but we're looking at f equals negative k, then we get this. But then when we go to actually divide by k, or divide by the negative k, these signs flip, right? So it's negative x squared over k minus y squared over k plus z squared over k. And if you look down here, that's a hyperboloid of 2 sheets. All right. So what we're doing is we're getting different types of surfaces. Sorry, that's an O. Two different types of surfaces depending upon uh, what the nature of the number that we set the function value equal to is. And of course, you change the k, you change exactly what it looks like, but we know that now in general, positive k, we get hyperboloid of 1 sheet. If it's a negative number, hyperboloid of 2 sheets. And then if it's 0, we get a cone. So let's go ahead and take a look at this. This is a different program that is a little bit more, it allows you to do a lot more than the 3D grapher we've been using, but I've just stayed away from it because as you can see, it's a little more complicated. But this is for a demonstration, so I think this will do nicely. So this first one here, this is where k happens to be, or the value I'm setting it equal to. This one happens to be where I think it's equal to 9 is what I'm remembering. So yeah, I set this one equal to 9. But this is one of the cases where it's a hyperboloid of 2 sheets, okay? Sorry, it's equal to negative 9, excuse me. Yes, this one's negative 9 because it's a hyperboloid of 2 sheets. Here's another one. This is where I set it equal to negative 4 for this particular graph. And so this one, we know based on our work on that page, should also be a hyperboloid of 2 sheets, but it will be a different hyperboloid of 2 sheets. And so you can see it is different, right? So this yellow one here and this gray one here, they are distinctly different surfaces. So these are different level surfaces from each other, but of the same type. Okay, now I'm going to do where it's going to be actually equal to 0. And so remember when we set it equal to 0, oh, sorry, no, I guess that one's my equal to 0. Lost track of my own graphs. There we go. When I set it equal to 0, remember we said that would form a cone, and that certainly looks like what that purple graph is. It's just a nice cone. All right, now we'll go ahead and set it equal to 4. And what did we say? When it's equal to a positive number, it should be a hyperboloid of 1 sheet. And you can see that there. And then finally, we'll add the last one. And so remember what these are. They're level surfaces. The domain of this function we're interested in, notice, is all real numbers, right? So let me go back to that real quick. Right? There's no restrictions on the domain here. So the domain is all of 3-dimensional space. And so when we're looking at these, what we're saying is any x, y, z that is on one of these surfaces, if you travel along one of these surfaces, the entire time you're going to have the exact same function value. It's not going to change throughout the entire thing. So this is the same idea as the level curves. But because we are now operating in higher dimensions, our domain's 3-dimensional, so therefore we have to have level surfaces instead of just level curves.